People have been studying chemistry forever, right? Um, and one of the ways that people have done chemistry over the centuries and millennia is to try and convert matter into different forms. Right? People have been doing that. In these days, it was called alchemy. Everything was centered around trying to make gold out of different elements and different compounds, or trying to convert it into gold. Really, when people started really being able to study chemistry is when they were able to control fire. Once they were able to control fire, they were able to cook. They were able to fashion metals into different forms. They were able to create pottery, because one of the steps in making pottery is to fire it in order to strengthen the material. Um, and one of the things about chemistry is that it is everywhere. It's all around us. How many of you, by show of hands, you can raise your hands again and with the little hand raising app, how many of you cook on a regular basis? Okay, see your hand went up, one hand, that's it. Okay. Oh, lots of hands. This is good. What's one of the ways that you know that your food is done? Anybody, just unmute. How do you tell? What's one of your techniques for telling when something is done?
Sometimes the color.
Color, okay, good. That's indicative of a chemical change when the color changes. What else? Anybody else? What about the smell? Right? If you're cooking something, and my theory is when you can smell it, that's when it's done. Like if I'm baking chicken or making whatever, if I put it in the oven, once I'm able to smell the aroma, that tells me that it's done, because cooking is also a chemical process, right? So if I can smell it, that means that there's some chemical change that's happened within that food item that has converted some matter in that item from one chemical phase to another, right? Look at the mask again. Tell me what else you see besides the gold. What else do you notice? Can you see that there are different colors here? This is a different shade of blue than that. That's red. This is the beak here is black. The eyes are black. Do you think that those pigments were discovered by happenstance, or do you think they were discovered and applied after some experimentation? What do you think?
Probably after some experimentation.
Yeah, it may have been accident. Sometimes you have discoveries that are accidental, but once you discover it and it's something that's useful, the next thing you do is to refine the process by which you acquire it, right? So these dyes are an example of the application of chemistry. The metal itself is an example of the application of chemistry. Different medicines, you know, the Egyptians were known for using they were known for extracting medicines from different plants and things like that. All of that is chemistry. So you'll hear chemistry referred to as the central science. Now let me pull this diagram up just to show you that how central chemistry is to everything. Let me pull this up here. All right, so we can say that chemistry happens anytime matter is manipulated, anytime it's converted from one form to another, or anytime it undergoes a chemical change that converts it from one type of matter to another. We can say that that's when chemistry occurs. So when matter is manipulated, either by a form change or a type change, right? But the point is that is to make you aware of the fact that everywhere you look there's chemistry. There's nothing that exists without chemistry. Even your socks, the nylon in your socks is a chemical, is a polymer, right? The nylon that holds your, if you're working out, your sports bra or your tights or your undergarments or your t-shirts or whatever, your spandex shirts, all of that is possible because of chemistry. So if you look at this diagram here, you can see how chemistry overlaps with just about every STEM discipline. And when we say STEM, obviously you know what that means, right? Science, technology, engineering, and math. But chemistry overlaps with environmental science. It overlaps with nuclear chemistry. It overlaps with food science. Most of our knowledge about overlapping with chemistry comes between chemistry and medicine, right? Because everybody has taken a Tylenol before, or an aspirin, or even taken the COVID vaccine, or some other drug. Maybe you got sick, you took antibiotics, whatever, right? But chemistry is central to even biology. If you're a biology major, chemistry is central to biology. If you're a chemical engineering major, chemistry is central to that. It's chemical engineering. And most of that entails learning the properties of elements and learning the properties of compounds such that you can scale up a reaction, right? You want to make, I remember when, I said this to the earlier class, when Teflon was a big deal, right? I don't know if you ever heard of that, but it's like a fluorinated polymer that they use to coat nonstick pans. I remember when that was a big deal. Well, Teflon itself comes from a fluorinated compound that is irradiated and polymerized. So you take it from one molecule of a compound and then you polymerize it so that many of those molecules attach together and with a polymer, right? The polymerization part, that's chemical engineering, because you have to scale that up so that you'll have enough of that polymer to coat 1,000,000 pans as opposed to only one pan, right? Chemistry and math also overlap because we use math in order to illustrate what's happening in the chemical world, right? That's why I talked about that on Friday about how chemistry, especially general chemistry, is really a lot of math, and other than that is more concepts. But we use the math to illustrate the concepts. So there's an overlap. So it overlaps with every discipline and under the STEM umbrella, just about. And this is just a small snapshot of how chemistry overlaps with other disciplines, but it's called a central science for a reason. All right. So now let's shift gears. And before we do that, can anybody chime in here? Tell me one example of chemistry that's happening where you are right now. How many? Well, let me not ask that. Anybody? One example.
Noodles in hot water.
Okay, so you are making noodles and you had to heat them up in order to. Did you add the flavor pack to the water, or was the seasoning already in it?
Pack.
You added a pack. Okay, so that's chemistry, because now you're taking the flavors in the flavor pack, and that's matter, and interacting that with the noodles that was separate from that, and you're putting those two together. Now it may only be it may be a physical change that's happening, but there's also a chemical change that's happening, because some of that seasoning is going to get absorbed into those noodles, right? And it's going to make a solution with the water that you're using. That's why you use hot water and not cold water, so you can get the flavor pack, the material to dissolve, right? So all of that is chemistry. Somebody give me another example.
Dyeing your hair like a different color.
That's a great example. That's a great example, because the dye that you use has to adhere to your hair, and the physical structure of your hair takes on that dye and changes the color. So that's a great example, right? Another example. How many of you just finished lunch? Anybody? I'll be quick so you don't fall asleep.
Me?
Right? So What's happening in your gut right now? Anybody? What's going to happen to those noodles once you eat them? Are they just going?
The food down.
It's going to digest. That's a chemical process. When the acids and enzymes in your stomach act on the matter that you have taken in, which in this case is a bowl of noodles or a sandwich or whatever, that's chemistry happening right there in your body. Our bodies are huge chemical reactors, right? There's chemistry happening in our cells. There's chemistry happening in our guts, in our blood, everywhere. So with that being said, again, let's talk about chemistry when it happens. Chemistry happens whenever matter is manipulated, either by that matter changing form or by that matter changing type, becoming a different type of matter. So we're going to talk about more about matter later on. I don't know if we'll get to it today, but we'll talk about that's chapter 1 is just laying the groundwork. All right. Let's move on to the scientific method. Right. The scientific method is what we use to help to explain our observations. All right. What's the when you think about the scientific method, tell me how you learned this as a high school student. If you're a second semester freshman, how'd you learn the scientific method as a high school student?
We learned that the hypothesis is based off like your opinion.
Okay. Your opinion on what? You're right, but what is that opinion on?
The experiment.
So something you have an opinion about something you observed, is that right?
Right.
In nature or in a lab or wherever. And then you develop a hypothesis. How do you test your hypothesis?
By conducting the experiment.
Doing more experiments, right? That's exactly right. So with the scientific method, there are basically 3 steps, right? And we're going to talk about, I have a diagram for this, but with the scientific method, you observe. Bad, sorry. You observe, you hypothesize, and then you experiment. Right? And sometimes the hypothesis part can come from an experiment. I remember as a graduate student, one of the projects I worked on, research projects I worked on, I actually discovered a new reaction that hadn't been done before. And then, so when I found that result, I observed that result, I had a hypothesis as far as what I thought happened. So what I had to do was go back and do more experiments to prove if my hypothesis was correct. So sometimes your hypothesis can come from existing data. Right? You can have hypothesis that comes from data that exists or something you observe in the process of doing an experiment. Maybe you get some anomalous result that you need to explain. So you have a hypothesis. So my hypothesis, the definition is a tentative explanation of my observations. That's my hypothesis, right? I see something and I need a way to explain it. This is what I believe caused this. That's excuse me, that's how I develop my hypothesis. All right, I'm making an observation, and then based on that observation, I'm saying, this is what I think happened, right? Now, here's the thing about a hypothesis. You have to prove it. In science is not such that, and this is really important, especially in today's climate where, people are decrying science. They don't want to believe people who've been studying, science forever. But science is really it's all based on the facts. What you observe and what you can prove is what matters. And so if I have a hypothesis and I don't back it up with any experimentation, which is the next step, then it is merely my opinion, right? That matters, because my opinion can be, if it can't be substantiated, then it, more than likely, it's just something that I pulled out of thin air. Science doesn't work like that. Science is based on facts, it's based on observations, and it's based on reality. And so the first step after your observation is to develop your hypothesis, and then to do the experiments to test your hypothesis. So your hypothesis is a tentative explanation. This is what I believe caused this observation. That's it, right? Then it's up to you to develop the experiments to figure that out, to figure out why you see what you see. So that's the next step in the process. So the scientific method is to observe, to hypothesize, and then to experiment. And then based on your experiments, you have after your experiments to test your hypothesis, right? If you see the data and you see that it is continually the same, then you can have what's called that information can become what's called a law. Those observations can become what's called a law. It's a summary of experimental observations. And normally those observations line up with the hypothesis. All right. So a law, and again, this is just laying the foundation. So there are going to be a lot of definitions. The first exam is probably going to be a bunch of definitions in addition to some calculations. So these definitions are very important. All right. So a law is a summary of experimental observations. Right. The next step is to develop what's called a theory. So a theory actually explains the observation. And a theory is testable. And a theory is also well substantiated, right? Let me hear some of you. What do you think about when you see the phrase well substantiated? Notice the key word is well substantiated. What do you think about when you see that phrase?
That makes me think of like educated guess.
Okay. It's a little bit past that, but that's the first step. Yeah, but it's a little past that. Go ahead, somebody else. When something is well substantiated, what does that mean to you?
It has some data to back it up.
Some data, some evidence to back it up, right? And so not only is a theory testable, like first comes the explanation. So this theory explains why this happens. Well, if that's the case, I should be able to go and test that theory and reproduce the results. So testable, and let me put this here in parentheses, reproducible. That's very important, right? It has to be reproducible. If I'm fudging the data, that's not science, right? But if the data is reliable and I can reproduce it every single time, that means that theory is well-founded. And well-substantiated means I have volumes of data to back up what I'm saying, volumes of data. Now, let me put this in context, because in today's, I guess in today's social environment, YouTube has proliferated. What is the other one? Clubhouse. There are a bunch of different platforms. People are on Instagram, people on TikTok giving you 30-second hacks, but everything that's said is not necessarily legit, right? This is what we talk about when we say well substantiated. You might be able to say that in 30 seconds on TikTok, but I need to see the proof. I need to see the data. I need to see how you came to that conclusion, or whether or not you just pulled it out of your head, right? And for everybody here, this is the essence of science, is to ask questions. If somebody gives you some information, you are well within your rights to say, how did you come to that conclusion? What experiments have you done to say that this is this and it's not that? You have to ask those questions. That's what scientists do, right? So something has to be well substantiated. And if it explains some natural phenomenon, we ought to be able to test it, right? So that's how things get, written in stone, even though science is fluid at the same time. Things change. Sometimes we have to go back and revise a theory based on the fact that we had information and we tested it this way, but now we have access to new types of tests. So if I tested it again and something changes, then I have to go back and do some revision. And you can't be afraid of revising, because it's not about always being right. It's about always being accurate about how you present things. So with the scientific method, observe, develop a hypothesis, and then test it. And then if what you test, if you are able to summarize those observations and they continue to verify your hypothesis, that can be a law, right? This is what happens. This is how, and we haven't gotten to this yet, but everybody here has heard of the law of conservation of energy. You might have heard it one way: matter can neither be created nor destroyed, right? What that really means is that when you have matter and you do some process to it to convert it into a different type of matter, there's no loss. So if I start with 100 grams of sugar and I heat that sugar and convert it into caramel, at the end of the process, if it's an ideal situation, I should generate 100 grams of caramel, right? I don't lose any matter as the matter is being converted from one type to another. That's a law. It's proven over and over again. It's been proven. And the reason why it may look like, oh, well, you lost something or the mass went down, is because we're not doing these experiments in a closed system, right? So if you have water and you boil it and evaporate it off, sure, if you are doing a distillation and you catch some of the water and wait and take the mass of it, it may be less because some of the steam didn't make it into your distillation trap, or some of the steam, escaped through whatever. But as a general rule, that's what makes a law, when you can take that information and see it confirm your hypothesis over and over and over again in various situations. So here's a chart that we can use, to illustrate the scientific method. Right? So you observe, that's the top. Let me erase that. Erase all this stuff. You observe, which is here. Right? You make an observation. Oh, I saw this happen. When I reacted these two things together, this is what happened. I wonder why. So now this is my hypothesis. When I ask the question why, I'm answering it with a hypothesis. I think it happened because this. So now you form your hypothesis, right? And the next step is to do more experiments. You don't just take a hypothesis and run with it and pass it off as fact without the experimental data to back it up, right? So you perform more experiments, make more observations. If they are not consistent with your hypothesis, right, then you go back and you either conduct different types of experiments, or you say my hypothesis was wrong and I need to study this from a different perspective, right? If your results are consistent with your prediction, then you've just helped science because you've added to what's already known. All right. And that's really important. That's why people are still publishing scientific papers to this day, 25 or 3,000 years after people started dabbling in trying to understand chemistry and understand how matter is converted from one type to another. That's why we still have scientific knowledge being, discovered on a daily basis, because people are still observing, people are still making hypotheses and experimenting to prove whether or not those hypotheses are accurate or consistent with what they observe, right? If you contribute to the body of knowledge, that's good. If not, go back to the drawing board, study it a different way, come up with a different set of experiments. And then, right, that observation can become a law after after those observations are constant, right? That means that you every time you run this experiment, you get the same thing, right? That's what we call a constant observation. Every time an experiment is done, you get the same outcome. Every time you test this natural phenomenon, you get the same outcome. That's when it can become a law. And then after much more additional testing that proves that hypothesis to be correct, the hypothesis itself becomes a way to explain what you observed. And that's what we call a theory. So the hypothesis and the theory explains right observations after much testing. So notice the hypothesis at first was what we call a tentative explanation, but once it becomes a theory, it becomes the accepted explanation, right? So it goes from being tentative to being accepted. Right, it's the accepted explanation for whatever that observation may be. All right, any questions? Anybody have any questions about anything before we move on? All right, how many of you, by a show of hands, excuse me, how many of you have participated in any type of research at all? Whether you were in high school or on a summer program or whatever, anybody? Nobody, wow. Hopefully would one person, okay.
Like research for an essay?
No, scientific research. I should have.
Oh, scientific,
qualified that.
oh, no.
Scientific research.
Oh, I was doing scientific research.
Okay, what was your topic? What were you studying?
We were studying tissue regeneration.
Say that again.
Tissue regeneration.
Okay. So did you have to develop a hypothesis regarding tissue regeneration, or was there something already accepted and you were just doing experiments that added to that body of knowledge?
Yeah, it was already a lab focus in the lab that I was in, and I had to come up with experiments to test that theory or that little subject.
Okay, cool. And that's how it works, right? Everything has to be tested, and that goes for anything that somebody throws at you, right? Anytime somebody throws out some new information, or somebody said, did Georgia Tech, Elijah? What type of research was that? Was that you, Elijah, that was just talking?
Nah, this Robbie.
Okay. What about Elijah? You want to share with us what you did?
Oh, me and Robbie was working on the same project.
Okay, at Georgia Tech.
Yes, sir.
That's awesome. Right, but again, research and science is all about information, accurate information. So if somebody says something on YouTube, ask them how they came to that conclusion before you just take it at face value. Because now we don't test stuff. We just say, oh, this person said it and they said they were an expert, but we don't really know that. So always ask questions. And if it proves to be true, that's wonderful. But if not, don't let somebody just give you something at face value without giving you, the background and why they came to that conclusion. All right. So let's talk about now, excuse me, the three domains in which chemistry is studied, or how we study chemistry. All right. So the three domains are, we study it at the macro level, macroscopic. We study it at the microscopic, and then we study it at the symbolic level, right? So if we're studying at the macro level, right, that means that what we're doing and what we're seeing is visible to the eyes, and it's also tangible. I can touch it, right? And that can be anything from a fabric that you are wearing right now that was developed in a lab somewhere. How many of you have have on either leggings or like I have on right now, a spandex undershirt to keep me warm. If you have on any of that, 9 times out of 10, if it's not Lycra, if it's nylon, nylon was developed or discovered by accident. It was discovered by a female scientist at DuPont by accident. But on the macro level, I can look at the shirt I'm wearing or the socks I'm wearing. I can see that, and I know that that is, you know, whatever that material is based on some chemical interaction that happened prior to it being made. So macroscopic is visible to the eyes. It's tangible. On a microscopic level, that's what we call. We say that it is invisible to the naked eye. All right, I can't just look at someone and see their cells. I can't look at a material and see the atomic structure of it. Right, that's what we mean by microscopic. And some things may only be conceptualized. And I said this to the earlier class, and I'll say it here. If we think about the atom itself and the subatomic particles that make up the atom, that's a concept, because we really have never looked into the structure of an atom. We have to conceptualize certain things because they are not visible, but we have to come up with a way to explain them. And so by conceptualizing them, we take them and in our mind, we're able to visualize what these things are, and then we develop a way to describe it. And in this case, this is a model of an atom. We're going to talk about atoms later, but this is just, for now, this is what we use as our atomic model. There's a nucleus in the atom, which is here. And in that nucleus, you have protons and neutrons, right? And outside the nucleus, you have electrons that orbit the nucleus. But that's a conceptual model because we have yet to see an electron, right? But based on what we know, we can conceptualize a model and say, this is what we believe the atom looks like, right? This is what we believe happens in the nucleus of an atom, right? So that's on the micro level. And again, we can't see that. It's invisible to the naked eye. All right, any questions about macro, micro? I'll leave this up to give you time to write it down. And again, these notes are gonna be posted in Blackboard. And I saved them from this morning, so I want to rewrite everything. But in the future, I'll probably just end up writing 2 sets of notes because I want you to be able to follow along and take notes as well. So yeah, so macroscopic, that's we study chemistry on the macro level, stuff that we can see, like color changes, like something that changes smell. If it undergoes a chemical change, the smell changes, the color changes, the temperature changes. Those are macro changes. But on a microscopic level, what's happening to produce those macro changes is the atoms from one type of matter are interacting with the atoms of another type. So that's what's causing those changes, but we can't see those. And then there's the symbolic level, which is the language of chemistry, right? It's how we talk about chemistry, and it's how we describe chemistry. If I write down Na, which I have here, right? That's not Na, if I'm talking about chemistry. It's the element sodium from the periodic table. That's the symbol for sodium, right? Because that's a symbolic way of illustrating sodium, especially when I'm writing out a chemical equation, right? C is the symbol for carbon, because symbolically that's how we illustrate or that's how we show what carbon is, right? By using the letter C from the periodic table. If I write down a formula, CO2, carbon dioxide, that's the molecular formula for carbon dioxide, which I illustrate symbolically, right? So all of these different domains intersect, right? On the macro level, we see things visibly, we see that, we feel them, touch them, experience them tangibly. But then on the micro level, although we can't see it, we know something is happening. And we may only be able to see that as a concept. We conceptualize that. And then on a symbolic level, that's how we talk about it, right? So when I write down an equation between sodium chloride and HBr, this is not a real reaction, but I'm just showing this. So symbolically, I'm showing that this is a compound consisting of sodium and chlorine. And this is also a compound consisting of hydrogen and bromine. And when I react them together, I get NaBr plus HCl, right? That's a chemical equation. And I illustrate that symbolically using the elements from the periodic table. All right, any questions about that? Any questions about, and we're going to talk about this in a second with the macro and micro. I have another diagram, as you can see, that we're going to dive into. All right, so let's talk about this. Let me erase this. All right, so let's look at this picture first. What do you see?
Ice.
Okay, ice, good. What else do you see?
Clouds.
Clouds, good. And what else?
Water.
Water, really cold water, obviously, right? But we see water in its liquid state, in its solid state, and then in its gaseous state. This is all macro. If you were in a boat, you could reach your hand down into that water and touch it. I wouldn't advise it because it's probably super cold, right? Or you can break off a piece of that iceberg and hold it in your hand. Or if you are hang gliding or parachuting or skydiving, you could pass through one of those clouds and actually touch it because it's macro. Everything here is visible to the naked eye and it's also tangible. You're able to touch it. So the solid water, gaseous water that makes up the clouds, that's water vapor, in addition to maybe some solid water. I'm sorry, some liquid water. And then the liquid water that makes up this lake or whatever this is. This is all macro. This is a macro depiction of water, right? Now look at water itself. Water is illustrated symbolically as H2O. What does that mean? Anybody who's already taken chemistry, what is H2O?
Water.
Right, but what does the formula actually mean?
Oh,
Hydrogen. Two.
Two hydrogens attached to an oxygen. Is that right? So we
Yes.
can depict this symbolically like this. And I'm even going to put in the electrons on oxygen because I know that when I draw a Lewis structure for water, this is what it looks like, right? So this is, but you can't see this here, but we know it's there. That's why we also study on the micro level. Right now, notice the H2O that's here, there's a G in parentheses next to it. What that means is that water exists as a gas, right? So this is the gaseous state, right? That moisture is a gas, it's a vapor, right? What do you notice about the water molecules? Because again, this is a symbolic depiction. So this, we call that a molecule of water. What do you notice about the molecules in here?
They're really spread out.
They're really spread out. And that's the hallmark of a gas, is there's a great distance between the molecules of whatever that gas is composed of. You can see that there's a distance between each one of these water molecules. Let me erase that. That looks sloppy, right? There's a distance between a great distance. And then when you look at the solid, which is ice, solid water, what do you notice about those molecules right away?
They're close to
They're in the
Closer together. They're closer together. They're more, which means that they are more rigid. That's why it's a solid, because those molecules are packed closer together than they are in a gas or in a liquid. So that makes it more rigid, and the molecules are more orderly. Right? There's a specific way that they pack in order to form that solid. What you don't see, which also is happening on the micro level, is the velocity of the molecules, how they're moving, how fast they're moving. In a gas, those molecules move very rapidly. I'll just say fast. I know that's a rudimentary term, but they move fast, right? In a solid, they move more slowly, right? A lot more slowly. That's why you don't feel vibrations when you touch things that are solid, right? Because the movement between those molecules is so slow that it can't be detected. All right. And then in a liquid, notice, what do you notice about the liquid? Look at how the molecular composition is of the liquid. Let me not say composition, because that's a different word, different term for a different thing. But look at the order, right? What's different between the liquid and the solid?
They're more spaced out.
A little bit more spaced out. And that, again, when we talk about the states of matter, which we will talk about later on Wednesday, that is the difference between macro and micro. You don't know the distance between those molecules just looking at that lake, right? But on a micro level, that's how we understand that, and that's how we study that. You don't know the distance and the rigidity and the structure of the ice, but on a micro level, you can find that out, right? You can take a crystal structure. If you can get that, keep it cold and keep it from melting, you can study it through crystallography. You can study solids through crystallography and see how the molecules line up or the elements line up. And the same with the gas. You can study gases as well. So again, all of this comes down to how we represent things and how we study chemistry. We study it on the macro level, we study it on the micro level, and we study it on the symbolic level, in that we use symbols to tell us what we're looking at and what we're observing. So with that, I got to stop because we are 4 minutes over time. Are there any questions?
Is your syllabus on Blackboard?
Yes, I just updated it to reflect the test dates. Let me say that before we got a minute. So the goal is to take a test every 2 weeks. And that way the information stays fresh and it keeps you on your toes. So the dates for the exams have been updated, and the syllabus is in the content area that's labeled syllabus. All right. And again, these notes are going to be posted to Blackboard as well. So, and the recording from this class session is going to also be posted. I'm going to send you a link for that. And you can